Today we're going to be talking about chemical equilibrium. Even though we're focusing on chemical equilibrium, it's still important to know the difference between physical and chemical equilibrium. Physical equilibrium is the equilibrium of a substance from one phase to another. And chemical equilibrium is the equilibrium of two substances. This includes the starting materials and products. What is equilibrium? It is when the forward and reverse reactions happen at equal rates and the concentration for both the products and the reactants is constant. This is done in a closed system so that no product can escape. Equilibrium does not yield only products, but instead some reactants remain after the concentration is no longer changing. Therefore, we can say when the reaction is at equilibrium, there is a mixture of reactants and products. Here's a helpful graph demonstrating the equilibrium for the reaction between hydrogen and iodine. I'll give you a second to take a look at it. Le Chatelier's principle. This principle states that if a dynamic equilibrium is distributed by changes in the conditions, then the equilibrium will shift in order to counteract the changes and restore equilibrium. This change can include changes in pressure, temperature, or concentration of the reactants or products, resulting in a shift in the equilibrium towards the opposite direction. Here's an example, and we're going to apply this principle to the reaction between hydrogen and iodine to find the forward and reverse reactions, as well as what direction the equilibrium is going to shift in. First, let's identify the forward and reverse reactions. In the forward reaction, hydrogen combines with iodine to form hydrogen iodide. The reverse reaction would be hydrogen iodide decomposing to form hydrogen and iodine. In this example, hydrogen is added at equilibrium. If this happens, which way do you think the equilibrium is going to shift? If you said to the right, you are correct. It is going to shift to the product side to use up the added hydrogen. But the equilibrium constant will not change, as changes in concentration do not change the equilibrium constant. Equilibrium constant. The equilibrium constant is represented by the symbol Kc or Kp for pressure. The equilibrium constant shows the relationship between products and reactants at equilibrium with respect to units. The equation for equilibrium constant can be written as, or for pressure. If Kc is equal to 1000 or higher, the reaction contains mostly products. If Kc is equal to 0.01 or lower, the reaction contains mostly reactants. If Kc is in between 0.001 and 1000, the reaction contains a significant concentration of both reactants and products. For the example I'm going to talk about later, I'm going to mostly be talking about concentration, so I'm going to be using the first equation rather than the one for pressure, but they are very similar with minor differences. Kc is the molar concentration of the starting materials and products, and Kp is the partial pressure of the starting material and products. The products are on the top and the reactants are on the bottom. The brackets represent the concentration and the coefficient is represented by the exponents. For reactions not at equilibrium, the reaction quotient Q will be used. It is it is equal to Kc at equilibrium. And if Q is greater than K, the reaction is going to shift to the left. And if Q is less than K, then the reaction shifts to the right. And if Q equals K, then the reaction is at equilibrium. Here's an equilibrium reaction between sulfur dioxide and oxygen to produce sulfur trioxide. The reaction contains the following concentrations on the right in pink. And now we're going to use these concentrations to calculate Kc for the reaction at temperature T by solving the expression written on the first line in pink. So plug in the concentrations that are on the right into your equation and solve for Kc. I got 4.3, so that is in between 0.001 and 1000. So we know that the reaction will have a significant concentration of both products and reactants at equilibrium. Now we have to use the reaction quotient to determine if the reaction is at equilibrium. Now that we have Kc from the example above, the same reaction has happened at the same temperature, but this time we have the following concentrations on the right in purple. And we're going to use this to calculate the reaction quotient, which can be calculated even if the reaction is not at equilibrium, but Kc can only be calculated at equilibrium. So plug in the concentrations that are on the right into the equation and calculate the answer. I got the same answer as I got for Kc. I got 4.3, meaning that this reaction is at equilibrium because Q and Kc are equal. Okay, so let's try an example to apply what we have just learned. At 2300 Kelvin, the equilibrium constant is 1.7 times 10 to the negative 3. For the following reaction, find the concentration at equilibrium. Okay, so we have our concentration listed in the question. We must calculate Q using the known concentration and compare it with Kc. To find if the system is at equilibrium, in which direction the reaction shifts to reach equilibrium. Then using an ice table, we must determine the equilibrium concentration of nitrogen, oxygen, and nitrogen oxide. So then you're just going to take the concentrations that are in the question and plug it into the equation that we just used on the last slide. And my answer was for Q was larger than Kc, so we know that the reaction is not at equilibrium. And also the reaction contains mostly reactants. Next, we're going to do the ice table. And once you've filled out the ice table, you're going to solve for x. You can solve for x by taking the square root of both sides, then multiplying both sides by 0.17 plus x, which gives you 0.0132. Then you use this to find the concentrations at equilibrium. And your answers are here in green. There are many examples of chemical equilibrium in everyday life, like a bottle of pop, for example. In the bottle is CO2 dissolved into the liquid. There is also a CO2 gas in the empty space between the lid and the cap, which is why you hear a sound when you open the bottle. The CO2 is constantly moving from a liquid phase to a gas phase, then back to a liquid phase within the bottle. There's no change within the bottle until it is opened because the system is at equilibrium. Without chemical equilibrium, life would not be possible. It plays a key role even in our own bodies. In conclusion, without chemical equilibrium, life as we know it would not exist, which is why it is important to understand what chemical equilibrium is, how the equilibrium constant can help us to understand the concentrations of reactants and products at equilibrium, as well as how to apply our knowledge of chemical equilibrium to the real world. Here are some practice problems that you can try if you'd like. I find they're really helpful to apply the knowledge that you just learned from my presentation.